Welcome back to ECE 320A. Homework 4 is due Thursday, and that is dealing with inverse Laplace transforms, and hopefully we will get through the material that's needed for you to complete that. The book has examples. I'm going to try to give you some other ways of computing the partial fraction expansion coefficients, and you could apply those in all these cases. I'm just illustrating it with the one case where it's case number 2 where we have repeated roots. And that's what this is the map of what I would like to cover today, and that is to really just review our earlier example that we talked about, which was with distinct roots. I'll simply scroll through that example, but I want it to be clear which particular partial fraction expansion coefficient you are using when you have complex roots, when you use a particular formula from the textbook. And we'll actually derive that. We're talking about the inverse Laplace transform, which allows us to work in the frequency domain, and that allows us to do algebraic manipulation instead of differential equation solutions. We can now jump into the frequency domain, play with this complex frequency variable S, manipulate that with algebra, find these partial fraction expansions, and then take those from the table back into the time domain, and that allows us then to maybe more easily solve or analyze electric circuits. But you can do this with many other systems, not just electric circuits. Last time I believe we started with this particular transfer function. And before you start performing partial fraction expansion, what's the first test you need to make on your ratio of polynomials? Before you jump in and get too excited or too involved, what do you need to make sure is true? The denominator degree is exceeding the numerator degree, or you have a strictly proper transfer function. If you do not, what do? You divide it out. You divide until your remainder has a degree strictly less than the denominator degree. In this case, we can just jump right in because the numerator is second order, the denominator is third order. And I have written the denominator in a way that it contains real coefficients, but that quadratic is written to emphasize that those are actually complex conjugate roots. And where are the roots for that denominator pole factor in square brackets? What value of S? I think I told you to go home and check that. What value of S will cause that bracketed term to vanish? And there's two, aren't there? There's two distinct complex values for S that allow that bracketed expression to disappear or to equal 0. And they are staring you somewhat in the face. S, the real part, needs to be -2. And that gets rid of that first squared piece. And then you somehow need to square something to cancel that 3 squared. Well, if you have a j3 or a -j3, because j is the square root of -1, when you square it, you get that minus sign, and that's the way that you cancel that 3 squared. Values of S equal to -2 plus and minus j3 are another way of writing that quadratic factor. And that's what I'm going to do here, because now I'm going to use the technique from case 1, which assumes we have real, or not real, but distinct roots. Obviously those last two are not real roots, but they are distinct based on where they are in the complex plane. The first one, and this is what I want to make sure that you're clear on, you're writing it, the factor is S plus 2 minus J3. But if you set that equal to 0 and solve it for S, that will give you a value of S at minus 2 plus j3, and that's the one you want to sort of concentrate on when you're finding the partial fraction expansion. You want to concentrate on the root or the partial fraction expansion coefficient associated with the factor that's on top of the pole that has the positive imaginary part. That's the one you want to key in on. Once you've found a sub 2, what do you know about a sub 3? Are they related? Do you have to go through this whole process again to find a sub 3? You can, but you don't have to, do you? If you've done your algebra right, what do you know about a sub 3 if it's on top of the conjugate pole pair associated with a sub 2? A sub 3 is the conjugate of a sub 2. And to conjugate a complex number, you just change the sign of the imaginary part, or you change the sign of the angle, depending on whether you have the complex number written in rectangular form or polar form. Is that all clear? Are you getting very comfortable? Does that make you feel warm and fuzzy when you're playing with complex numbers? You should, because that's what you're going to be playing with now. You should know complex numbers if you don't know ladders. Okay, good. And I've just tried to give you a diagram so that when you see these factors, you're starting to visually put those in the complex plane. When you have this factor s plus 1, that's corresponding to a pole at s equal to minus 1. And if you looked at the transient behavior associated with that, what do you get out of a1 over s plus 1 when you inverse Laplace transform? If it doesn't right now, by the time we have our exam, this just needs to be rolling off your tongue, or at least rolling off of your pencil. So that's e to the minus t, isn't it? E to the minus 1t, to emphasize that the pole is at minus 1. And we can find a1 from our approach that we talked about last time. We multiply the left-hand side by the factor that's below the a1 expression or term or coefficient. That gives us then everything in f except the s plus 1 factor in the denominator. And then we evaluate that at the value of s where that s plus 1 factor would vanish, or when it's equal to 0. Plugging in those numbers, and if you don't want to play with the complex numbers, you can remember that that factored form of s plus 2 minus j3 times s plus 3, or s plus 2 minus j3, condenses down to this real expression, s plus 2 quantity squared plus 3 quantity squared. And now you can plug in s equal to minus 1, and that's pretty clean in the denominator, and you don't have to play with all of this complex algebra if you don't want to. If you do, that's fine. It should give you the same result. And we, I think, derived that last time. So we have 1/2. Now to find a sub 2, we do exactly the same thing. These are distinct roots. We multiply the left-hand side, the capital F of s expression, by the factor that was underneath a sub 2. And that factor was associated with the pole that's in the second quadrant in the complex S-plane. That then cancels that factor in the denominator, but it leaves all the other factors. The s plus 1 factor is there, and the twin or the cousin, whatever we want to call that, the one that's below the one that was above, is still remaining. We didn't cancel it. But then we evaluate that expression at the value of s that causes this factor on the left that I've indicated multiplying f of s, whatever s is that causes that to vanish. That's the value of s that you substitute into that expression and evaluate for a sub 2. And a sub 2 can be and probably will be a complex number. And if you go through the algebra, which, that's kind of a fun exercise. Or you can plug it into your calculator. If you have a calculator, if you have shelled out the dough for a calculator that does complex numbers, let that do it for you. Just make sure you don't miss key. This gives us then an a sub 2, a little bit bigger than 1. And the angle, if you look at the numerator, minus 8 minus j21, what quadrant is that point in? The numerator, minus 8 minus j21, in the middle line for a sub 2. That's in the third quadrant, isn't it? And the other value is also in the third quadrant. I think maybe I have an error in that expression. I was checking my work and it's not checking, is it? Because what am I seeing wrong here? The magnitude looks okay. The 22, it's a little bit bigger than 21, but what's minus 8 minus j21? If that's now in the third quadrant, that should be between, let's say, minus 90 and minus 180. So now 150.8. Where did I get 11.8? I don't know. Anyway, I think the result is correct. Oh, it's 110. Thank you. See, you want to make sure you key it in or you write it down. So what I did is I misplaced my decimal point. That makes me feel better. Thank you. Somebody on the way over here said they needed to get here early so they could put their mind or take it down to neutral, or maybe that's what I said, and I said my mind's probably still in neutral. Obviously it is. So there is maybe a corrected version. Okay? Thank you for the help. I need all the help I can get. And what's a sub 3? That one we don't have to do much to get, do we? Once we found a sub 2 and a sub 2 is correct. A sub 3 is the conjugate. We just negate the sign of that. And now what we want to use in order to make sense of this next equation in blue, which is, let's say, the partial fraction expansion with the appropriate coefficients, it'd be nice if we knew how to convert that phasor into something that we can put into the time domain. And all we have to do is remember that 1.184 at an angle of 50.8 is equivalent to a magnitude of 1.184 e to the j 50.8. That e to the j is giving us this magnitude of 1 at an angle of 50.8 degrees. We're going to now use that, but what we're going to key in on is we're going to utilize mostly that partial fraction expansion coefficient above the factor associated with the pole that's in the second quadrant. And that's what I'm trying to emphasize with this highlighted yellow in the second quadrant of the complex S-plane. That's where the pole is. That's the one that you use when you're going in the table. If you look up this pair in the table, you want to make sure that you're using the partial fraction expansion coefficient above that particular pole factor. Then you get your angle correct. In this case, that angle was a positive 50.8 degrees, meaning if we simply used our knowledge of S plus A being e to the minus AT, then we would have something like this in our time domain expression. But I might not give you all 10 points on the solution if that's how you left your answer. It might only give you 5, or no, 1, maybe a half. Need to get my decimal point in the right space, right? A half a point out of 10 if you leave it in that form. Because that's not the form that's in the table, is it? But now we're going to derive that result that's in the table by using our relationship for rewriting that phasor in terms of this e to the j, theta. If we do that, once we have all these e's, we can start combining the exponents. The e to the minus 2t is contained in both of those right-hand terms, and then I'm going to factor out what's inside, or what multiplies or scales the square root of minus 1, or the j term. Is everybody okay with this step, from the middle equation to the bottom equation? All we've done is rewrite the phasor in terms of e to the j theta. As I said, e to the minus 2t was common to both of those terms on the right. Magnitude was the same. That was the 1.184. And now I can rewrite the complex exponential as e to the j something, which is 3t plus 50.8, plus e to the minus j, that same expression. And that's looking really good, if you remember Euler. Because Euler, that's saying, oh, that's 2 times the cosine of what's in that angle bracket, or inside parentheses. Meaning we can now, and hiding over here on my infinitely wide paper is this t greater than or equal to 0. But now, on the exam, just picked up a car. Where was I before I started driving off? Now, on the exam, what you can do is you don't have to do all these intermediate steps. You can go immediately this. You have a magnitude of 1.184 and an angle of 50.8. Now you know that that goes into a cosine. You just increase the magnitude, you double it, you say 2 times the magnitude, e to the minus 2t, that was the damping on this sinusoidal variation, cosine of 3t, and here you have a plus 50.8. That was the angle of a sub 2. And that's all you have to write down on the exam. You don't have to rederive, you don't have to show where that's coming from. We now know we're all okay with that progression of data, or that derivation. And the 2 in front of the cosine comes straight from Euler. If you remember Euler, Euler was saying, what am I using now? Now I'm saying that the cosine of x is equal to e to the jx plus e to the minus jx over 2. That's what I'm using to obtain that. Is that okay? So I know that Euler gives me cosine x is e to the jx plus e to the minus jx over 2. And what I had in the blue bracket was simply the jx's. So that gives me twice this cosine. That's where that 2 is coming from. So I'm going from there, knowing that fact, Euler, to immediately writing down twice the magnitude, and now I can simply write down that expression for my partial fraction expansion coefficients. Questions on that? We can make some observations relative to what we've done with these distinct roots. One is that a sub 2 and a sub 3 were just complex conjugates of each other. And the other one was the fact that if I now have this need to go into the time domain, given the frequency domain, I thought that's what was getting put back on the table, and then I go over here and there's a bunch of keys. So if you're listening to this, you're wondering, what is he talking about? But if you listen to this after seeing it, then it makes a little more sense, right? I apologize if you're listening to this, but you're already asleep anyway. We're 20 minutes into the lecture. So you're just hearing this voice. And it means nothing. Where were we? Oh, trying to inverse Laplace transform. So I need to wake you back up, or wake myself back up. Here's a sub 2, and in general, that's s plus alpha minus j beta. And where is that pole located? In what quadrant? First, second, third, or fourth? So let's say alpha and beta are both positive. Then that factor, that pole, is going to be in the second quadrant. This one will then be below it in the third quadrant. And that's A3, which is A2 star. But now if you have your partial fraction expansion in that structure, and you found a sub 2, if you've now calculated a sub 2, you can immediately write down that that's 2 in the time domain, the magnitude of a sub 2, e to the minus alpha t. That alpha gives you the decay. Cosine, you're shaking at what frequency? Beta. So you're oscillating at beta, and then you have a phase shift relative to the origin of theta sub 0, where I'm now using the fact that a sub 2 is a complex number with an amplitude of a sub 2 and an angle of theta degree. Is that clear? The notation may be a little bit different, but this is consistent with equation 1264 in the most recent edition of your textbook on page 449. And you can also find that in addition to other transform pairs in table 12.4, table 12.3 on page 453. Questions on this technique for distinct roots? Simply multiply through by the appropriate factor and evaluate at the value of s where that factor vanishes. And you can find all of these coefficients in the numerator. Gets a little bit more interesting for case 2. And this is the situation where you have repeated roots. For example, if we had something like f of s equaling a numerator n sub 2 of s over s plus p1, let's say squared, s plus p sub 3. And I'm going to assume that n sub 2 is of what order? strictly less than 3. It's going to be 2, 1, or constant, right, as far as a polynomial in S, in order to continue. But now, what does my partial fraction expansion look like? How many terms do I have? I should have 3 because I have a third order in the denominator. So now, depending on how you label these, I think this is consistent with how the book does it. Suppose that I now put A1 on top of S plus P1. Then you actually have to keep knocking that power down, and each one is going to give you a factor in your expansion. You don't just write S plus P1 squared. You actually have to pick up the S plus P1 factor also. And if you had a third order, you would have S plus P1 cubed, a factor in the denominator, plus an S plus P1 squared, plus another factor S plus P1. Here we're going to have A sub 2 over S plus P sub 1. And we can't forget the one that's actually distinct, which is the S plus P sub 3. Questions on how that happens, or that process? If you had S plus P1 to the 4, you would just step down. You would have 4 terms associated with that. And you would just incrementally go down, reducing that exponent. Now the trick is to find those A's. And that's a little bit more challenging when you have repeated roots. A sub 3 is not much of a challenge, is it? That's associated with a distinct root. So you can find this using the case 1 approach. Meaning A sub 3 would now be this S plus P sub 3 times whatever we called that. I guess it was still F of S. And what value of S do we evaluate that expression at? Minus P3. Or, knowing how the denominator is factored, we now have S plus P1 squared, because we've canceled the 1 factor, the S plus P sub 3 factor, and we evaluate it when S is equal to minus P sub 3. Questions on that? That's straightforward. That's from our distinct root case. We can also use that same approach for the coefficient, to find the coefficient associated with the highest power of the repeated root, if that makes any sense. Let me see if I can word it another way. You can also, the case 1 formula works for the coefficient associated with the highest power of the root. Meaning, which of these coefficients, A1, A2, and A3, am I talking about? And your odds of a correct answer are actually 2/3, aren't they? Because there's 2 distinct roots here. Meaning you could say, well, A sub 3, we just found it. We used case 1. That's true. That's one of the correct answers. So now it's between A1 and A2. So if I'm Monty Hall, I've already opened up one of the doors with a gate, or with a goat. Now it's your turn to pick the winning door. A1 or A2? I want to find the coefficient associated with the highest power of the root. That's the A1. And I can just use the same approach that I've used for the distinct roots. I can find A1 by multiplying the left-hand side by the factor underneath A1, which is S plus P sub 1 squared, F of S, and I evaluate that minus P1. In terms of the way that I had parameterized F, that's just N sub 2 over S plus P sub 3 evaluated at S equal to minus P1. Meaning now we found A1 and A3 the first way, case 1 way. Now we need to find A sub 2. To find A sub 2, there are a lot of different ways to do this. And remember, the partial fraction expansion is true for all values of S. And we're going to use that to our benefit. There are many different ways or many techniques for finding A sub 2. But in finding these that you can't find, what we're going to assume is we've already found the ones that were easy using the case 1. One can assume in this example that A1 and A sub 3 have been determined from the above technique. And by that I'm meaning the case 1 technique. Before we find A sub 2 or go through the cases, let's just sort of remind ourselves with a more specific example what we have and what we will be looking for when we have repeated roots. Suppose I give you an F of S that's now 2S plus 1 over S plus 1 squared S plus, let's say, 2. We now know the partial fraction expansion structure. That's going to be A1 over S plus 1 squared. And now we just continue to reduce the power on that repeated factor until we get down to the power of 1. And that should have been an A sub 2 over S plus 1. Those are not the same coefficients. We have an A1, an A2, an A3, depending on how many we have. And now we have an A sub 3 over S plus 2. If on the exam I said, give me the structure, only the structure, I'm basically saying do not calculate A1, A2, and A3. Just give me the structure for the time domain expression little f of t. Then you would write down an expression that contains these coefficients, A1, A2, and A3. And what do we see? We have A1. That's a little bit different, isn't it? Because we haven't inverse Laplace transformed some quantity squared. So let's go to the others. Maybe you go, I'm going to punt on that one. So here's A2. What's A2 look like? That's e to the minus 1t, isn't it? That 1 here is right there. And the a sub 3 piece And that's true for non-negative values of time, where this 2 is there. Now what's different is this first piece. Because of that square, now we're actually going to have t raised to some power. In this case, the power is 2 minus 1, so I'm not even really writing it down. It's still that e to the minus t. The t is coming to us because we had a something squared in the denominator, and the minus 1 is again consistent with that pole at minus 1. So now we're going to have this t e to the minus t term because of this s plus 1 quantity squared factor. What does that do as t gets big? T e to the minus t, does that blow up? We have a ramp, and that's getting multiplied or scaled by this damped exponential, e to the minus t. Which is dominating? T or e to the minus t? E to the minus t. So this is going to go up and then come down as far as the time response behavior. But it's going to eventually start decaying with this e to the minus t shape. The last two terms, I think, are pretty clear. Now, let me just sort of do an aside. I've really gone aside chasing a rabbit before we get back to these different ways of finding a sub 2. But now I want to talk about the structure when we have repeated roots. And let's just concentrate on real repeated roots. So the structure for repeated real roots. Meaning if you were putting together a table, we have just demonstrated that if we had something like 1 over s plus 2, what would that look like in the time domain? And we're dealing with one-sided Laplace, so we're just going to switch that on with the unit step, the u of t. That means that's true for t greater than or equal to 0. That's what that's meaning. What if I now had so now we have to, it gets a little bit more interesting. We do have a t squared term, e to the minus at u of t, but we also have a factorial, where it's that 2 is really 3 minus 1, is where that's coming from. Meaning if you wanted to generalize this, and on the exam I gave you something like 1 over s plus a to the 50, that was a joke. I'll probably only give it to the 48th power. Not a problem. In general, let's say that's raised to some n plus 1 power. Then you have in the time domain 1 over n factorial t to the n e to the minus at u of t. And that's as far as I want to chase that rabbit. That's as far aside as I want to go. But that's now the structure. Each time you have a bigger power of that denominator polynomial, you get a higher power of t in the time domain. We probably won't go much bigger than something raised to the cubed or to the 4th. But then you're going to get a t squared or a t cubed in the time domain result. Questions on that? Let's now get back to the example that we left, and that was this f of s equaling 2s plus 1 over s plus 1 squared s plus 2. How many poles do you have in that expression? It's not really a trick question, but it could trip you up a little bit. There's actually three, right? It's a third order. You have two of those poles sitting on top of each other, one at -1, another one at -1, and one at -2. You have three poles. You're looking for three terms, and we just said we're going to say that we have an a1 over an s plus 1 squared, an a sub 2 over s plus 1, and an a sub 3 plus 2. A sub 3, what's in the denominator? If I'm now solving for a sub 3. And at what value of s do I evaluate? And if I do that, I end up with 2 times -2 plus 1 over -2 plus 1 squared. So I end up with 1 in the denominator and a -3 in the numerator. Which of these remaining coefficients can I find? A1 or A2? A1, the one associated with the highest power of the repeated root. To find this, I now have 2s plus 1 over, I've now multiplied through by what was in the denominator of that a sub 1 expression. What's remaining then is simply the s plus 2 factor, and I evaluate that at the location where the a1 factor root vanishes, or at s equal to -1. This is now 2 times -1 plus 1 over -1 plus 2. Again, we end up with 1 downstairs and -1 upstairs. Now let's finally get into these different approaches for finding a sub 2. And I'll try to number those. Here's number 1. And these are sort of going, these are not necessarily discussed in the book. Maybe the last one is. I'm holding it off because you can always go look at it in the book. But I said that the partial fraction expansion was true for all values of s. So why don't we pick a convenient value of s? We really just have one unknown in this expression now because we found all the others. Why don't we pick a convenient value for s and solve for that one unknown? That's the first approach. Select a convenient, and that's really up to you. So a convenient value, whatever you think is convenient, for s. In this case, if we go back to our expression, what can we not do that will, what could we pick for s that wouldn't help us? If we pick one of these roots, that's not going to give us anything. That will maybe give us infinity equal infinity, and that's not going to tell us anything. So we want to stay away from s equal -1 and s equal -2. Those are not convenient. A lot of times I look and I say, do I have a pole at the origin? Do I have a s sitting down there? And if I don't, I'm going to plug in s. That'll get rid of a lot of, or s equals 0. That will get rid of a lot of the s's. That's what I want to do here. So this is a nice first guess, but you want to make sure that that's not one of your poles. So now that convenient value needs to be something other than a pole. But now we have f of s evaluated at that 0. On the left-hand side, we have 2s plus 1. And then we had s plus 1 squared, s plus 2. And then on the right, we had a sub 1, which we've already calculated to be -1, s plus 1 squared, plus a sub 2, s plus 1. plus a sub 3, which was minus 3, s plus 2. Questions on where that formula came from? That's just the partial fraction expansion evaluated at s equals 0. S equals 0 is a convenient value of s. And you could have picked s equal 1/2, s equal 2, s equal minus 2. No, not s equal minus 2, but s equal minus 3. If you think that's convenient, go for it. Just make sure your algebra is correct, and it will give you the correct answer. If we now solve this for a sub 2, if we look on the left-hand side, we have 1/2. We have minus 1 plus a sub 2 minus 3/2. And what's a sub 2 end up being then? If we solve for it, we have minus 2.5 on the right. So we add 2.5 to both sides, and we had 1/2 already over there. A sub 2 is now 3. And now we have our result. We found a1 was minus 1, so that's minus t e to the minus t, plus a sub 2 e to the minus t, a sub 3, which was minus 3 e to the minus 2t, t greater than or equal to 0. That's one way of finding a sub 2, or solving for a sub 2. Here's another way, and I'm going to call it the limiting expression. And I'm assuming you're familiar with limits, or you're comfortable with performing these limiting arguments. The first thing we want to do is multiply both sides of our partial fraction expansion formula by s. Then we take the limit on both sides as s goes to infinity. Take the limit as s marches off to infinity. And the hope is that everything is going to start cleaning itself up, and we'll just have a sub 2 equal to something. We can solve for a sub 2. That's the approach. So let's apply that limiting expression technique. We had our left-hand side, which was f of s. That was 2s plus 1 over s plus 1 squared s plus 2. And then we had a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. And if we want, we can replace these with what we know they are. This was minus 1, and this was minus 3. Now what we want to do is we want to multiply both sides, so we're still trying to do step A. We want to multiply every term by s. So I'm going to put an s there, I'm going to put an s there, an s there, and an s there. That's okay. Now what I want to do is I want to see what happens on both sides of the equation when I let s march off to infinity. On the left-hand side, and here now what you're doing is you're comparing. If you now had s plus 1 and you let s go to infinity, well, let's do something else. Let's say we had s squared plus s plus 1, and we let s go to infinity. Which of those three terms is going to get bigger quicker? S squared. So now we're focusing on the highest power of s in the denominator and the numerator when we look at these limiting arguments. On the left, the numerator is of what order? Since multiplying by s, it's now second order, isn't it? What's the denominator order? 3. So now we have s squared over s cubed, which is effectively 1 over s, and as we let s go to infinity, what's 1 over s going to approach? 0. So the left-hand side now becomes a fat 0. About the next term, the first term on the right-hand side is s over, comparing the largest power of s over s squared. That looks like 1 over s, which when we let s go to infinity, we get another 0. So now we've eliminated a1, haven't we? We don't have to worry about what it might equal. Now look at the middle term on the right. S times a2 over, and you always have to keep track of the coefficients of the leading powers of s. What's its over? A sub 2s over, what's the highest power in the denominator and its coefficient? Times s, isn't it? So now as s goes to infinity, the numerator slides off at exactly the same rate as the denominator, and what are we left with? A sub 2. Is that clear? What about the next term? We now have minus 3s over s. As s marches off to infinity, those s's are moving at the same rate, and we're left just with minus 3. What's a sub 2? That was pretty easy, wasn't it? So now we get the same answer that we had before. That's a second approach. Again, there's many different ways of doing this, and we still haven't gotten to the one that the book uses, and we aren't yet there with our third one either. So the third one is the one that probably is the most fail-safe, is to just find a common denominator. It's the most brute force. It might be a little more difficult to compute, but the machinery, it's easy to turn the crank. You now have this partial fraction expansion. Now you basically put it all over the same denominator again. And you're going, why did I even do this in the first place? But now you have unknown coefficients in the numerator. First step is to obtain a common denominator on both sides. You already have one on the left. That's already over the same denominator. Now put the right-hand side back over a common denominator after you factored it. Now what you do is you compare. The denominators are the same, aren't they? On the left-hand side and the right-hand side. Now the only thing to make them equal is to equate the numerators. And to equate the numerators, you need your polynomials to be the same, which means you need to equate the coefficients in those polynomials on the left side and the right side. This will make more sense as we go through an example. But now we're going to equate the coefficients of like powers of our complex frequency variable s in the numerator. And that will give us m equations in m unknowns, and we can then solve that. Solve the equations for the unknown coefficients. Let's use this approach on our example since we know the answer in the back of the book. Right? So our transfer function is this 2s plus 1 over s plus 1 squared plus, times s plus 2. So now we have 2s plus 1 over, should have written it down here to begin with, equaling a1 over s plus 1 squared plus a sub 2 over s plus 1 plus a sub 3 over s plus 2. And the first step is to actually put all of those terms on the right over the same common denominator that's on the left. So now we're just doing algebra. A1, does it need to be changed? If the result of this needs to end up being a1 over s plus 1 squared, then we would need to scale a1 by s plus 2. Is that okay? What about a sub 2? We need to fill it up with what's missing down below. We need an s plus 1 factor and an s plus 2 factor. Plus a sub 3, what does it get scaled by? Is it clear where those came from, those terms? And now we can simply multiply these out. We have s squared plus 3s plus 2, and we have s squared plus 2s plus 1. And if we multiply all of that out and collect the coefficients of the similar powers of s, we end up with a sub 2 plus a sub 3 s squared. Because a1 is not scaled by an s squared, is it? Plus, now which ones scale s? We have an a1, we have a 3a sub 2, and we have a 2a sub 3, all scaling s. And then we have our constant term. Bummer, amount of room. But down in that slot, I now have 2a1 plus 2a sub 2 plus a sub 3. And all of that is over a common denominator. Is it okay where those came from? What? This is a turn the crank approach. Meaning now all we have to do is plug this into our calculator, essentially. We can now equate coefficients of the like powers of s. Or we can actually sort of back substitute and solve this in sort of an iterative fashion if we wanted to. But if we compared the coefficients for s squared, what's on the left? 0. So now we have 0 is equal to a sub 2 plus a3. So now we know a2 and a3 are negatively related if we wanted to do that. But if we just do it the brute force way, now we have 2 on the left, and that's equal to what was scaling s here, which was a1 plus a sub 2 plus 2a sub 3. And our constant coefficient, or s to the 0, was a 1 on the left, and that was equal to what I ran out of room with before, 2a1 plus 2a sub 2 plus a sub 3. And now you're happy that you're taking 310, right? Now ECE 310, you have 3 equations and 3 unknowns. Now you have some linear algebra, right? And you hope the equations are consistent. Have you talked about that? So you want these columns, or you want your right-hand side to be in the row or the column space Are you talking about that? Range space, null space? Yes, no? All right. So what we want is the following. We now build up our equations if we wanted to put it into our calculator. We now have something times a1, a2, a sub 3 equaling 0, 2, and 1. And the top row was a2 plus a3. The second row was 1a1 plus 3a2 plus 2a sub 3, and that was equal to 2. And then our last one was 2a sub 1, 2a sub 2. And now you were wondering, when are we ever going to use this linear algebra? You use it all the time. And we've now used it for partial fraction expansion. Right? So if you wanted to call this some mx is equal to b, where x is now a, now you could invert m if it has an inverse, and hopefully it does. And you would find that it's minus 3, or minus 1, 3, minus 3. And that's another approach for finding these partial fraction expansion coefficients. Technique 3, ECE 310, right? Okay, let's jump into the textbook. The last one you'll really enjoy then, if you like that one. We'll call this the derivative method. If you didn't like my linear algebra, now we'll go into calculus. So now if you want to do this, you can see the textbook for the different pages. There's the real and complex root case on those 3 pages. Suppose now we have this f of s equaling n sub 2 of s over s plus p1 squared s plus, what was I calling this, p sub 3. So that I now have some a1 over s plus p1 squared plus an a sub 2 over s plus p1 plus an a sub 3 over s plus p sub 3. All right, here are the steps. You have your seat belts on? All right. And your helmets. Don't want to have any accidents. So now we multiply through in this expression by the highest power. This should look familiar, of the repeated root factor. In this case, we're multiplying every term by s plus p sub 1 squared. Then, and this is why you studied calculus in 7th grade, now you get to differentiate. So you differentiate all these terms with respect to x, or s as in Sam. So differentiate with respect to s. Then we substitute into that expression s equal to its root location. So evaluate at the root location. And that will now allow you to solve for this unknown coefficient a sub 2. Let's see what this looks like in an example. Step A. We multiply through by the highest power of that factor. That's what we have on the left. And then on the right, what do we have? We have an A1 plus an A sub 2 times S plus P1. We've canceled one of those. Plus A sub 3 S plus P1 squared over S plus P sub 3. We okay with that expression? Now we need to differentiate. We differentiate this expression S plus P1 squared times f of s. And I won't do that just yet. But now we differentiate A1 with respect to s. What's that produce? What are we trying to do? We're trying to find a sub 2, so when any of these go away, that's a good thing, right? Constant, when it differentiates with respect to s, is gone. Now we differentiate the second term, a sub 2s plus a sub 2p1. Differentiate that with respect to s. Now we've isolated a sub 2. And we now, if we want to, let's just go through this since I know you enjoy differentiating. Differentiate the next term with respect to s. Now this is a quotient, isn't it? I never liked quotients. I just broke it into a multiplication problem. So now I have a multiplication of two terms. One's in the denominator and one's in the numerator. So if I differentiate the numerator, I now have, so this is now 2a sub 3 s plus p1 times the derivative of s plus p1 with respect to s, which is 1, and that's over my denominator. The derivative of the second term, which is downstairs. So I now have s plus p sub 3 to the minus 1 differentiated. I get a minus that all's just treated as a constant. That's my first term. And now I have s plus p sub 3 squared times the derivative of s plus p sub 3, which is 1. Is that okay? I've differentiated. I haven't done that curly bracketed term yet, but I'll save that for you to do tonight. Maybe, if we don't get there. Step 3, or step C, was to do what? Go back to our recipe. And now we're not even sifting, are we, with the recipe, if we were baking? No. Now we're evaluating. Boy, lost the group about 30 minutes ago, didn't I? Gonna have to get you back somehow. In the next step, I evaluate at s equal to minus p1. What's that do for me here on these two right-hand terms? Those s plus p1 factors help me now, don't they? Because when I evaluate those at s equal to minus p1, they vanish. And my denominators are okay, because I have distinct roots. So the only thing I have left then is step D, which says that a sub 2 is now equal to the first derivative of s plus p1 squared of s. And I need to evaluate that once I've done the differentiation at s equal to minus p1, and that will be my a sub 2. In my example, when I multiply by s plus p1 squared, I end up with the numerator that I started with over s plus p sub 3 evaluated at s equal minus p1. I've canceled the s plus p1 squared factor in the denominator. Questions on that? I know you want to see this, so I'm going to provide it for you. Let's look at the general expression. I just did one when I had a squared term, didn't I? What if I had a 48th power, like I said you might have on the exam? How would you find all those a sub j's? In general, for an nth order root, what do we have? Now this capital F of s is equal to, let's say, n of s over s plus p sub 0 to the n. Then my partial fraction expansion is going to be a1 over s plus p sub 0 to the n plus a sub 2 over s plus p sub 0, 1 less than that, n minus 1, and I just keep going. I get down to a sub n over s plus p sub 0, meaning I've reduced my power in the denominator to 1. You can actually obtain a formula for those coefficients, those a sub j's. The formula is as follows. A sub j, a sub 1, a sub 2, a sub 3 is equal to 1 over j minus 1. And in that case, maybe that's not a good, since we're in electrical engineering, j is not so good. Maybe we need to make that an L. A sub L is equal to 1 over L minus 1 factorial d to the L minus 1 ds to the L minus 1. So we differentiate L minus 1 times this lovely expression, s plus p sub 0 to the n, f of s, and where would we evaluate that? And I'm not meaning in your car or on when you're texting. No, you don't text and drive, so you probably shouldn't do these partial fraction expansions while you're texting or while you're driving. You can do it while you're texting, just not during the exam. And this is true for L in values of L. Questions on that? Let's do an example with the derivative method. I'm just so excited I can't hardly contain myself. Everybody's papers are going into their bag. What's up with that? Here we are. V of s is s squared, let's say, plus 3s, and now, for whatever reason, I've mixed it up. Now we have s plus 1, and I have s plus 2 cubed. What's the partial fraction expansion look like for this? Let me save that last one for s plus 1. So now let me do this one. This needs to be over cubed, doesn't it? Then I have a sub 2 over s plus 2 squared plus a sub 3 over s plus 2 plus a sub 4 over s plus 1. Which of these can I find immediately? If you're now out of time on the exam, 1 minute remaining, which of these do you solve for? A1 and A sub 4, right? Those are the two that would work immediately using the case 1 approach. Then you would have to go through the derivative method or some other, pick a convenient value. What would maybe be a convenient value of S here? 0. And you might have to find another convenient value of S because you may need two equations. Because now you have A sub 2 and A sub 3. We may or may not pick up at that point on Thursday. But this is what you need for your homework. Bless you.